there's one thing in common among all those examples, and that is that it is a certain, you attempt to sum over an incredibly large number of incredibly small quantities. And that's the common theme. So I think that's more productive to think in terms of accumulation process, as opposed to always thinking about area. Even though at the beginning of this chapter we start with the computation of area. All right? But I hope that this Riemann-Sun concept, which you learned last semester, reminds you the fact that the definite integral really is the accumulation process, accumulating a lot of small quantities. All right, so that's the first example. The second example, the area of the region between x is equal to sine y and x is equal to 2x over pi. No, 2y over pi. 2y over pi. And then, and with the condition that y is greater than or equal to 0. How do you draw the first line? If I say y equal to sine x, what would you say? Right? But this is not y equal to sine x. This is x equal to sine y.
So y is equal to sine y.
Yeah? Remember that guy there? Right? Okay, so it's on the other side of the transparent board. And what that guy would see as a sine function, right? Curve of sine function is, I mean, you want that guy to see a sine function. Right? Sine function would be like this, right? Then, what do you think? Wouldn't that be something like this? All right? Make sense? Mm-hmm. Right? Okay. All right. The next one, this one is a linear thing. Is that right? It's supposed to be a line. So when x equal to 0, y is equal to 0. When x equal to what? Y would be, when y is equal to pi, x will be 2. When y is equal to pi over 2, x will be what? Huh? I'm looking at a second equation. When y is equal to 0, x is equal to 0. When y is equal to pi over 2, x will be 1. Is that right? That is good. That's a good point, right? So x equal, I mean, as far as this guy is concerned, this is 0, is that right? Mm-hmm. And this is what? Isn't that pi? Isn't that 2 pi? Is that right? And so where's pi over 2? That must be this mark. And y equal to pi over 2, x equal to 1, wouldn't that be this point here? All right? So this line here passes through this point as well as the origin. Right? And so what I'm going to do is I'm going to connect it like this. You see that? So that is the second one, which is x equal to 2y over pi. And So you want the area in between the straight line and the curve, and all the while you want to be such that y is greater than or equal to 0. So you don't want to be below ground, right? So which area are you talking about? Would you be talking about this area? Right? What are you going to do? So I want you to calculate that area.
Horizontal slices?
Horizontal slices, very good. You know, if you use vertical slices, it will eventually work, right? But it will be a more difficult integrals to deal with. You're going to have arc sine function to deal with. Okay, you will eventually prevail. You will do it, right? But precisely because of the form it takes, we decided that it's much easier if you do horizontal slices. So, with the experience of this, I'm going to erase it. Then I'm going to immediately set it up. When you say horizontal slices, then you imagine that you have a large number of wrong color. You know, slices this way. So you have a scan line, right, which you bring from the bottom, right, gradually move it up. In the course of doing so, you stop at various places, right, and then that divides the whole area into a lot of very thin horizontal slices. So what I'm going to do is that because I control the scan line this way, right? So at first it is at a high 0, and I gradually push up until you reach this level, which is what, pi over 2? Is that right? So this is pi over 2. This mark here, pi over 2. So what I'm going to do is I say, just to remind myself, y is 0 to y equal to what?
Pi over 2.
Pi over 2. That's the process. That's the process. And along the way, a typical stopping point would be like this. Okay? So let me magnify it. You're going to see something like, you know, here's the region, right? And magnify it. And in between, you stop at, you know, you push the scan line to this height, temporarily stop, and then keep pushing again. That's the next level. Right? So you have a very thin horizontal slice. Then the y controls the height, right? And y is the controlling variable in this process. So a typical slice will have a typical y. And for that typical y, there are two x values, right? X controlled left, right. So this x value and a greater x value. This x value is falling on this line, is that right? So that x value is determined by y, which is that? 2y over pi. Whereas this point to the right, this n, you know, depends about exactly which point you're talking about, but it's roughly, it's the, you know, you have an x value and a y value, and y is being controlled, x is being controlled by y. In what manner? That one, right? So this larger y, x value is sine of whatever this y is. So what I'm trying to say is that you have sine y on the one hand, that is the x value, the greater x value, and 2y over pi on the other hand, that would be what? The smaller x value. So you have greater x value, a smaller x value. Take the difference. Isn't that the length of that slice, roughly speaking? All right? Okay, so I take the difference. And then, so that's roughly the length of that horizontal piece. And what is the width?
dy.
What is the height? dy. And that should be consistent with this here. So y equal to 0, y equal to pi over 2. Because the controlling variable is y. That's why I thought in terms of y here. Got it? That's it. And then usually you don't write this y here because you assume that whatever this d, whatever it is, right? dy, so you assume that this means y equal to 0 anyway. So usually we don't write it. But at first, you probably want to remind yourself by explicitly writing y equal to this, y equal to that, as opposed to x equal to whatever. So this is set up, and then the rest is counted. All right, so let's quickly do it. This one is what? Negative cosine y, correct? And from what? 0 to pi over 2. And then minus what? 1 over pi y squared, correct? And from 0 to pi over 2. So this one becomes negative cosine pi over 2 is what? 0, right? Minus negative, right? Minus and then negative what? Cosine 0. What is cosine 0? 1, right? And then the top minus, that's because this minus, 1 over pi, what? Pi over 2 squared, correct? Right? And then you subtract. Subtract what? You still have this minus sign there, and therefore it becomes what? Plus. Plus what? Well, 0. Right? So I'm done. The answer therefore is 1 minus pi over, wait a minute. Oh, pi over 4, sorry. I was pausing, and how could that be? It's negative. Pi over 4, not pi over 2. Pi over 4. And that's the answer. Not too bad, right? Okay, much easier than chapter 7, right? Okay, isn't it good to have chapter 7 behind? You're not off the hook yet, though. I have particularly in mind the 7.8. 7.8 I only give you 2 simple problems, right, on the exam. And I told you I wasn't going to emphasize that, right? But it turns out that even though that was relegated to the last sections of chapter 7, but I guess I think I told you before that in my opinion that's actually a very important section in the application. Sometimes dealing with physics problem, for example, you have a lot of integration problem which goes from some finite number to infinity. And it's not really a exceedingly complicated kind of integrand, but nevertheless,